In this video, we will introduce the idea of how we can find the surface area of a surface of revolution. So the idea is that if we start off with a non-negative function, so something like we see pictured here, from x equals a to x equals b, and we form a surface out of this. That is, we take this curve and we rotate it around the x-axis. So if we think kind of what that would look like, I want to draw the mirror image, and when we rotate this around, you think of this as being a surface. So it's not a solid, as in it's hollow, but you have everything kind of on the outside. And we would like to know what its surface area is going to be. And once again, I've just kind of given us the formula for surface area. We would take the definite integral from a to b, 2 pi the function, multiplied by this square root quantity we saw when we were calculating the length of the curve. But once again, let me give you just a small bit of intuition in terms of where this is coming from. We consider taking this interval from a to b, breaking it up into a bunch of these subintervals, and we approximate what's going on with this ith subinterval. So we're thinking, from xi minus 1 to x sub i, what is the approximate surface area there? So what we would do is we would trace up to our function, and we'd say, okay, if we approximate the function here with a straight line instead of a curve, and we revolve this around, what is going to be the approximate surface area of this small piece? Well, to approximate that surface area, what we want to do is just think about, okay, for this maybe right circle here, what is its circumference multiplied by how we approximate it, the length of this small segment? So we think of the f of x as representing, in a sense, kind of the radius that we see in that ith slice. And we think of this square root term as coming from the length of this small segment. So the length of that small segment is corresponding to that square root term. So then you add up what's going on over all of the slices, take a limit as n goes to infinity, you get this integral. So I just wanted to give you a small bit of intuition in terms of maybe where this formula comes from. But once again, the important thing here is, for a given example, can we apply this formula? So let's do that. Let's find the area of the surface obtained by rotating y equals square x from 0 to 4 around the x-axis. So in this example, the function that we have is f of x. So the formula for surface area is going to be the definite integral from 0 to 4, 2 pi times the function, and I'm just going to write the formula out, multiplied by the square root of 1 plus f prime x squared. So we know what f of x is. It's the square root of x. So this is the integral from 0 to 4. And I'm going to go ahead and pull the 2 pi out front. So square root x. And what we need to do, and we'll just do this to the side, is figure out what is f prime x and what is f prime x squared. So if f of x is the square root of x, that is x to the 1/2, f prime x is 1/2 x to the minus 1/2. So f prime x squared is going to be 1/4 x to the minus 1. So we'll say 1/4 times 1 over x, or just simply 1 over 4x. So underneath the square root, we have 1 plus 1 over 4x. And at first glance, this really does seem like quite a difficult integral. But the idea is, in order to evaluate this, somehow we're going to need to be able to simplify these terms. So what I'm going to go ahead and note is that when you multiply together two square roots, you just multiply together what's underneath the square roots. So we can really take this x and have it hit each term in there. So this is 2 pi, the definite integral from 0 to 4. Combining square roots, it just becomes x plus 1/4. And now this is looking, I think, substantially better. What we need to do is just evaluate it via substitution. So using a substitution, we can say u equals x plus 1/4, so that du is equal to dx. And we need to change our limits of integration as well. So that lower limit of integration, when x is 0, u is 1/4. And when x is 4, our upper limit of integration, u is 4 plus 1/4, which is, so 4 is 16/4, so this would be 17/4. So this becomes 2 pi times the definite integral from 1/4 to 17/4 of the square root of u du. Because just to double check here, the x plus 1/4 was u, the dx is du. And this resulting integral is much simpler to evaluate. We know the antiderivative of square root u. That's u to the 1/2. 1/2 plus 1 is 3/2. So this is 2 pi times 1 over 3/2, or 2/3, u to the 3/2 from 1/4 to 17/4. So that's really a 17. So we have 2 pi times 2/3, which is 4 pi over 3. We plug in 17/4, so that would be 17 over 4 to the 3/2. We put a minus sign, we plug in 1/4. And I don't see any quick or obvious simplifications here, so we will leave our solution in this form. So let's look at a second example and see some familiar algebraic techniques. So in this case, our function f of x that we're considering is the square root of 4 minus x squared. So we need to know what is the derivative and what is its square. So differentiating here via the chain rule, the derivative of square root x is 1 over square root x. So we have the derivative of the outside, so 1 over 2 square roots, evaluated at the inside, multiplied by the derivative of the inside. So in this case, the 2 in the top and the bottom cancel, and we have minus x over the square root of 4 minus x squared. So when we square f prime, it's nice because the square root term goes away. We'll get the top squared over the bottom squared. So let's put this together now. So the surface area that we want to calculate is the definite integral over how the x values vary, minus 1 to 1. What we are going to integrate is 2 pi times our function multiplied by the square root of 1 plus f prime squared. So 1 plus x squared over 4 minus x squared. Now once again, at first glance, this looks like it could be a difficult integral. But remember, when you have a square root times a square root, you just take what's underneath the square roots and you multiply them together. So we're going to combine into a single square root, and we're going to let that 4 minus x squared hit each term. So pull out the 2 pi. Now we have a single square root, which will be 4 minus x squared plus x squared. So almost too good to be true. It ends up being just 2 pi times the definite integral from minus 1 to 1 of the square root of 4, which is just 2. And recall what a definite integral is. It's a enclosed area. So in this case, if we think about what enclosed area we would like to find, we have the curve y equals 2, and we would like to know the area enclosed from minus 1 to 1. So that's a rectangle with base length 2 and height 2. My picture's not to scale. So the value of this integral is simply going to be 4, thinking in terms of areas. So 2 pi times 4 is 8 pi. If you prefer not to think about it more from the intuitive geometric perspective, you could also easily evaluate this definite integral with the fundamental theorem of calculus.